Hello everyone, welcome back. Before we start off with the simple linear regression validation, let me again give you a recap on what exactly we have finished. I would assume that you have that existing R script file which we had partly completed, and also my uh, sheet, the Word file that has the content in it. So ensure that you have these two things, and let's start off. So let me finish off activating these two libraries, the dplyr and the ggplot. If your workspace is empty, please ensure that you have read the placement data frame. And since we were only doing simple linear regression between degree percentage and MBA percentage, let me select only those two columns that we wanted. Structure regression, we have already done this. I'm just reactivating those things. I'll skip the visualization part, and let's build the model between degree percentage and the MBA percentage. Now once the output is ready with you, you will realize the intercept. This is my beta naught 41.109 and 0.319 is beta 1. So if you refer to the Word file, you will realize how do we interpret this 0.319 is for every 1% increase in degree percentage, the MBA percent will increase by 0.319% on an average. Right. So this is where this we had already built, and how does it look in terms of the plot? So on my x's I have degree percentage, on our y we have the MBA percentage, and this is the line that this particular model has fit, the blue line part that you're seeing. These are our 215 data points, and you realize there are a few points on the line, there are a few points closer to the line, there are a couple of other points which are far away from the data point, and this is what is leading us to the error part of it. So we will understand more about this as we go forward today. Right, and to see the entire summary part, we said we'll use the summary command. So today's task is to go through all these part, whatever is the output in the summary, and we wanted to also extract certain values from the model that we have fitted. So I told you this model 1 that we have fitted has a list of 12 items. Now we will end up learning at least 5-6 of these outputs, but let's finish off extracting those values that I want. I wanted the y hat, the predicted value, to be stored in MBA p hat. So this MBA p hat, if I show you the head part of it, so these are the predicted values of y based on whatever model that we have fitted. And if you want to compare this with what exactly is the actual part, so these are our actual values. You can compare this with the predicted values. There are certain values which are closer, and there are certain values which are far away from the actual value. So you see 58.8 has been predicted as 59.6, fairly okay. 66.28 is 65 predicted, whereas in the third observation 57.8 the predicted value is 61.5. So there's ups and downs, some positive, some negative errors is what we realize. And then we said the mean value of the prediction and the mean value of the actual should be same. So we finished off checking whether the predicted value is equal to, the mean of the predicted value is equal to the mean of the actual values. Right. So if I still want to understand what is that mean value, the mean value is 62.27. All right. So we have extracted the predicted value. Similarly, I would want to extract the residuals. Residuals, you understand, is the error. The gap, whatever you are seeing between actual and predicted, is stored under residuals. So what we are doing now is, in mod 1 residuals, we have extracted the residuals of our model, and let us see what it contains. So this minus 0.8, whatever you are seeing, is basically 58.8 minus 59.6, y minus y hat. And we said mean is 0. It's basically because the sum of the residuals is 0. The positives and the negatives cancel out. So this is where we had stopped. And let's continue from this further. So this has given you a fair recap on what we had done, and let's move on further. So we started off understanding that concept of validation of the SLR model, and we said there are 5 things that you need to validate. I'm assuming you are looking at the word file part of it. Now in validation part, there are 5 things that we need to validate, and the reason why I need to validate is so that whether I can use this regression model for practical applications for prediction purposes basically. Right, so there were those 5 things that we had to validate on. One was coefficient of determination, one was the hypothesis test for regression coefficient, and the third was ANOVA. The fourth one was about residual analysis, and the last part was outlier analysis. Let me display the summary back again. So this is what is the model, and we are out to validate this particular model. Right, so the first part, if you look at, is the coefficient of determination. The symbol that we use is R or R square. This is where I am in that output now. This particular part is what we are trying to understand. So you see 2 things there, multiple R square and adjusted R square. We will discuss on these 2. So the coefficient of determination measures the percentage of variation in Y explained by the model. What exactly does that mean is the R square is the proportion of variation in the response variable explained by the regression model. The value of R square would lie between 0 and 1. So higher the values implies a better fit. There is no minimum threshold value for R square. However, if you still want to find out what should be the minimum value for given significance, you can derive it using the relationship between F statistic and R square. For the sake of from the mathematical point of view, R square is in simple linear regression, R square here is nothing but the square of the Carl-Pearson's coefficient of correlation. So in our example, you see here R square is 0.619, and adjusted R square would be more meaningful when we learn the multiple linear regression part. So if I want to understand this 0.1619, what exactly it means is that the model that we have built explains 16.19% of the variation in MBA percentage. So whatever equation that we fitted, y is equal to beta naught plus beta 1 x, this particular beta naught plus beta 1 values, whatever you have got, is able to explain 16.19% of the variation in MBA percentage. So there's a whole lot of percentage which is not explained. So this remaining variation is due to other factors that were not included in the model. Right? So we have only remember we have only included degree percentage. So with degree percentage in the model, I am able to explain 16.19% of the variation in MBA percentage. Right. And I've given you a small note there. A higher R square value is not necessarily a good indicator of the correctness of the model. So there could be some spurious relationships also into picture. And the adjusted R square is a statistic that modifies R square by incorporating the number of explanatory variables and the sample size. Right. So since here I have only one explanatory variable, let's not get detailed part into this. As soon as we start multiple linear regression, we will come across more of this adjusted R square. As of now, I've simply interpreted based on the R square value. So this is what is the R square part of it, which is the coefficient of determination. It's capital R and a square to it. The second validation part, let's get into it, is the hypothesis test for regression coefficient. So we have this beta naught and beta 1, and you will see those values here in the output. Our beta naught was 41.1 and beta 1 is 0.319. So the regression coefficient beta 1 captures the existence of a linear relationship between the response variable and the explanatory variable. So if we say if beta 1 is 0, we can conclude that there is no statistically significant linear relationship between the two variables. So the usual way in which we were framing hypothesis, for the t-test, whatever we have done earlier, on the same lines. So if I have to have the null and alternative hypothesis stated here for SLR model, my null is going to be that there is no relationship between x and y. That means I am saying beta 1 is 0. That is my null, beta 1 equal to 0. Alternative, I'm going to say there is a relationship between x and y. That means beta 1 is not equal to 0. So go back again, check null, there is no relationship. No part, remember, always comes in the null hypothesis. So there is no relationship. When I say there is no relationship, that means you are saying beta 1 is 0. So that being the null and alternate, we are not going to interpret the t value part as we have been doing. I am simply going to interpret based on the p value part of it. So in our example, you will see the p value for degree percentage is very small, almost 0. In simple language, since the p value for degree percentage is less than 0.05, we are going to reject the null, and since I'm rejecting the null, I'll be able to conclude that there is a significant evidence suggesting a linear relationship between degree percentage and MBA percentage. So this is a valid value 0.319, right, because the p value is less than 0.05. So now what we have tested is on the regression coefficient. I also need to, let's move on to the third point there. If you're referring to the material, the third point talks about testing for overall model. Now in this case there is only one variable, so your overall model and testing for an individual variable works out to one and the same. But let's anyways get introduced to how do I test on the overall model. So ANOVA is what we use. The F test gets applied. So I'm on this particular line here now, the F statistic and its corresponding p value. So keep an eye on these values and let's get introduced to what we are testing here. So we say using ANOVA we can test whether the overall model is statistically significant. Now remember, as I told you, for SLR the null and alternative hypothesis in ANOVA and t-test are exactly same. So since they are exactly same, you'll also realize there's no difference between the p value that you have got for your regression coefficient and the p value that you have got for the overall model, because the model has only one variable, right? So after I have tested for this one variable, I actually don't need to test for this overall model. But let's get introduced to it, because for a multiple linear regression we will anyways have to take care of that part. Okay, so since the p values are same, how are the hypotheses being framed for an F test? In general, for a null we'll say there is no statistically significant relationship between y and any of the explanatory variables. We could have multiple explanatory variables. In this case we have only one. So the null here is there is no significant relationship between y and any of those variables. Alternative, not all regression coefficients are 0. That means in null, remember, you have stated something like, if you write in terms of an equation, you have stated beta naught is equal to beta 1 is equal to beta 2, as many betas as you have, all those are equal to 0. Whereas alternative, you are going to say not all are 0. So invariably you are saying there are some with 0, but there are others which are not 0, right? So in short, 0.2 and 0.3 for an SLR would be same. So if you finish off checking for your individual variable, it's as good as checking. You don't need to actually check for the overall model. The p values are going to remain same. All right. Okay. And the fourth validation, this is the most important part. The fourth part is my residual analysis. So residual, again for a recap, the residual is the difference between the observed value of the dependent variable and the predicted value. Remember, observed value is denoted with the symbol y and the predicted value is denoted with the symbol y hat, right? So the gap between them, the difference between them, y minus y hat, is my residual or error. So each data point has one residual, could be positive, could be negative, and residual analysis becomes important because you need to check whether those assumptions of the regression models have been satisfied. Remember, I've built only the regression model. Now can I practically use it depends on whether whatever assumptions apply for a regression model are being met or not, right? So now if you're looking through the content, Uh, Residual analysis is basically performed to check those four things that I've shown you there. The first of them is whether the functional form is correctly specified. We assumed a linear functional form. So is that functional form actually applicable in this case or not? And the second one, whether the residuals are normally distributed or not. That is y minus y hat should be normally distributed. The third thing that I need to check is whether the variance of the residuals is constant, right? So we have been doing this. We have been talking about homogeneity of variance. Here specifically, you are going to call that particular concept as homoscedasticity. Practice would help you pronounce, right? And the fourth and the last part, whether there are any outliers, right? So in order to check all these four things, what I would need access to is the residual plots. So let's plot it first. So now you already know what residuals are. So I'm skipping that one small part. If you still want to apply that, you're okay with it. You know the gap between the blue line and any of those black dot is my error, is my residual. So if you simply still want to see it, we already have this part in place. I can copy this ggplot thing here, and to this I'm again going to further add if I want to see those red lines that we had seen during the example stage. So I'm using the geom segment, and I'm saying the aesthetic that I'm defining is from x end is degree underscore percentage, and draw a segment from x end to y end is what I'm saying. Y end should be up to MBA p hat, the blue line part. Okay, and just to differentiate this line, I'm going to say let the color of the line be red. So it could be any color that you would like, and the size of that thickness, let it be as 0.3. Alright, so it's an extension of whatever plot we have done. X end is equal to degree percentage. Right. This should solve it. So it gives you a more clear picture in terms of what exactly. So all these red lines that you are seeing is my residual part of it. So my actual value is this particular black dot, and the value on the blue line is my predicted value. So this gap is mine, right? So this was only to help you basically understand these are the errors that we are now talking about, right? Let me close this part. All right. So how do I go about doing those four things that we mentioned here? I would need those diagnostic plots. And I'm going to use the plot command, the simple plot command. So whatever is there in model 1, I'm plotting it. Remember, we have already plotted when we spoke about ANOVA. We didn't do all the four plots, so we looked at only one particular plot. So now moment you run this plot command in the console, you see it says hit return to see the next plot, right? So one option is finish off executing all the plots. The margin is too large because my view is more. Now it should help me. Hopefully this should solve. All right. So with zoom should be more clear. There are 4 plots which come out of those 7 or odd plots that are usually generated. So the plot command is going to generate 4 plots. This was the first plot. It says hit return. So let me finish off generating all the 4 plots, and then we will individually refer to each of those plots. All right. So these are the 4 plots that we have got, and let's take a closer look at these plots. So the first of the plot that I have is the residual versus fitted plot. Where do I use this residual versus fitted plot? Let's go through that. So this plot is used to check the linear relationship assumption. Remember the first point that we said there was the functional form of regression is correctly specified, and we have specified a linear relationship. So an approximately horizontal red line, you see a red line here on the plot, an approximately horizontal red line without any distinct patterns is an indication for a linear relationship. So there you don't see any pattern. These are my residuals. I'm not seeing any pattern as my actual values or fitted values increase, right? So uh, there's no curve or anything like that. There's no pattern. They're simply spread out, right? So any pattern here would indicate incorrect specification of the model. The specification that I've said is do a linear thing. So since there is no pattern that is coming out, that's fair enough for us. So this suggests that we can assume linear relationship between our degree percentage and the MBA percentage. If this residual plot indicates a non-linear relationship in the sense if this plots show you some kind of a curve. So if I'm showing it to you on the screen. So if you see a plot being plotted in the form of an inverted U or a U part of it, then whatever form linear doesn't apply. So we will have to actually look at a non-linear part of it. So since we don't have that problem, that gets sorted out. So I've given you a small note there in case your residual plot indicates a non-linear relationship in the data, then we can do those non-linear transformations slightly beyond our scope as of now, but for the sake of understanding, remember. So instead of using the value x directly, remember x is my degree percentage, I can do a log of x, or I can do a square root of x, or I can do x square, and that would depend on what is the kind of shape that I am seeing in those residual plots. So here, since I don't see any distinct pattern, our first of that assumption is satisfied. That means the functional form is correct. Now if the independent variables and dependent variables are linearly related, then the relationship between the residuals and the predicted values will be linear, right? So this you're seeing a relationship between the predicted values, the fitted values, and the residual. So if this is linear, I can go back and conclude saying that my independent variable and dependent variable are linearly related. Clear with the first part? Let's move on to our second plot. Let me get access to it. We have used this plot multiple times to check normality, the QQ plot. So let's look at whether the normality assumption is getting satisfied or not. So this particular plot, the normal QQ plot, is used to examine whether the residuals are normally distributed. So as we know, it is good if the residuals follow the straight dash line. So you have a line here, and if all my residuals exactly are on the straight line, that's perfectly normal. But there are small deviations here, nothing much to bother. So in our example, we see here most of those points fall approximately on the reference line. So it makes good for us to say we can assume normality. That means moment I say I can assume normality, whatever t test and f test that we did, hypothesis in step 1 and step 2, those tests are valid. The results of those tests are valid. So in case this residual plot does not follow this normal or approximately normal distribution, it is going to put a doubt on the validity of the model, right? So in the sense that result of the t-test cannot be trusted, right? So I cannot trust the outcome of the hypothesis test, right? So I can trust that a hypothesis of t-test and the f-test because these are normal, all right? So this was my second of the plot, which was used to check for normality. And let's move on to the third plot here. My third plot is the scale location plot. Now this scale location plot, also called as a spread location plot, is used to check the homogeneity or the variance of the residuals, right? So homoscedasticity. So this plot is going to show us if the residuals are spread equally along the ranges of the predictors. So this is my predictors, the fitted values. And the failure to meet this assumption will result in unreliability of the hypothesis test. So is it good? Is it not good now? How do I go about checking? It is good if you see a horizontal line This red line is what I'm talking about. It is approximately horizontal with equally spread points, right? So as my predicted values are, as I go across my predicted values, the spread between here is more or less, right, equal. Right? So it basically says that a horizontal line with equally spread points is a good indication of homoscedasticity, right? So if this is homoscedasticity, what is the opposite part of it? It's called heteroscedasticity. So if there is heteroscedasticity, then we can expect a funnel type shape in the residual plot, in the sense at lower values the residuals might be closer, and as you go ahead you get a V kind of shape, right? So imagine a funnel that I'm saying is a V shape. A funnel shape would indicate that the variance of the residuals depends on the value of the independent variable x. Let me show you clearly what exactly is the funnel that I'm talking about. So this part here, the spread, the residuals are, as I go higher onto my fitted values, the residual values are spread on those lines. The funnel for me here would be something like this. If I see a tilted V, or another way around, if I see a tilted V on this side, if you see that kind of shape, then I don't have that homogeneity of variance being satisfied part. Okay. Alright, so this part, the scale location part, is my third of the plot. Let's move on to the fourth plot. Let me access the fourth plot here. The fourth plot is my residuals versus the leverage plot. Now this residuals versus leverage plot is used to identify influential cases. Influential cases are extreme values that might influence the regression results. Remember when I had showed you the plots, we were talking about if there are some influential observations, uh, the slope of the line might actually change, right? So I need to take care whether my data has any influential points because of which my line is tilting to a certain direction, right? So go through that part of the explanation on what exactly are outliers and the high leverage points. After we've understood the outliers and the high leverage points is where we would come across discussing this residuals versus leverage part. So outliers are observations whose values show a large deviation from the mean value, that is y minus y bar is large. So for an observation, if y minus y bar is large, you would want to label it as an outlier. So in simple language, an outlier is a data point whose response, the y value, does not follow the general trend of the rest of the data. So this particular observation's y value is kind of away from the rest of the data is what we mean. So presence of an outlier can have a significant influence on the value of the regression coefficients, that is beta 1 in our case. Observations whose standardized residuals are greater than 3 in absolute values are possible outliers. Right, so that's, if you count that as a rule, now you'll see in our example there are no outliers which exceed this 3 standard deviations. So this is my 0. I'm looking at absolute value either on the positive side or on the negative side. All my standardized residuals are within this 3 part of it. Is that okay? So what we are basically saying is there are no outliers which exceed 3 standard deviations in our case. The second part is to understand on the high leverage point. Data point has high leverage if data point is basically an observation. An observation has high leverage if it has extreme predictor x values. Leverage value of an observation measures the influence of that observation on the overall fit of the regression function. So outlier was, now if you've understood the difference, the outlier was talking in terms of y, the leverage point is talking in terms of x. Right, so leverage values of more than, I've given you a small formula thing there, of more than 3 into p plus 1 the whole thing divided by n is treated as highly influential. The p there is the number of predictors and n is the number of observations. So in our case I have only one predictor, so basically what I'm talking about is 1 plus 1 would be p plus 1. So 3 into 2, 6 divided by 2 and 5, which is the value 0.028. So in our example, if you look at 0.028 should be somewhere here, right? So this is, if this is 0.03, 0.028 could be close by here. So I see some values which I say are high leverage. So these are points with high leverage over here. And mostly the observations with high leverage and high residuals can be removed from the data set. So residual part is well under check, but I don't have any observation which have both high residuals as well as high leverage. So this has high leverage, but it doesn't have high residual. So forget as of now, we don't need to do any alteration to our data set. So outliers and high leverage data points, now since we have understood them, both put together have the potential to be influential. Right? So we have not talked about an observation being or a data point being influential. We simply understood outlier, what is outlier and what is a high leverage point. Now outliers and high leverage points, data points have the potential to be influential. So I need to check if my data point is influential or not. So we'll have to investigate further to determine whether they are actually influential. If it is influential, I would need some adjustments to be done. Remember, not all outliers are going to be influential in linear regression analysis. So what do we use is a metric called as Cook's distance in order to determine whether in order to determine the influence of a particular value. So this Cook's distance will help me decide whether a value is, whether a data point is actually influential. So this metric Cook's distance defines influence as a combination of leverage and the residual size. So it is taking both into consideration, the leverage part and the residual part, and then it is calculating a measure called as Cook's distance. So in our example, the data don't present any influential points. So if there were some data, see, the Cook's distance would be represented by a dashed line. I don't see a dashed line at all in my chart. That means there are no data points which are highly influential. So this is like the legend part of it. So I don't see a dashed line, but where would I actually see a highly influential observation? Let's read through that part. The Cook's distance line, that is a red dashed line, are not shown on the residual versus leverage plot here because all our points are well inside of the Cook's distance line. So I don't see the Cook's distance line at all. When data points have high Cook's distance, these are generally located at the upper right or the lower right corner of the leverage plot. So if I'm talking about data points with high Cook's distance, I would see them here at the upper right or at the lower right. Right. So we can also see the if I specifically want to see the Cook's distance, I can do a plot of the Cook's distance thing. I've given you the code there. It's plot number 4. Remember, there are various plots which get generated. The 4 plots that we saw was those which were automatically generated. Now if I specifically want to look at the Cook's distance, what I am saying is extract the plot number 4 from my model. So in model 1, whatever is my plot number 4 is actually a plot for the Cook's distance. Okay. So by default, the top 3 most extreme values are labeled on the Cook's distance plot. So the 7, 26 and 197. This comes by default. These are the top 3 most extreme values. Right, but I don't have to worry about them because you realize if I there's no influential observation. I don't see anything here. As we go forward, we'll come across an example where you would see the dashed line part of it. All right. So what exactly did we do now? If you understand, we built a simple linear regression model. Right. We used the LM function to come out with that model, and then we got across a simple linear regression line, MBA percentage is equal to 41.109 plus 0.319 times of degree percentage, and we checked whether, so instead of using check, we validated this model using those 5 things. We checked how is the coefficient of determination, that is the R square, fairly okay, 16.19%, not bad. Then we checked whether my beta 1 is significant, so we used the t-test, we used the hypothesis test to check whether B1 is significant, and we also learned how to check the overall significance of the model using the F part of it. So we said F overall also the model is significant. The next part that we did was we went through this residual plots in order to validate our regression model assumptions. So there were 4 assumptions that we had made, and one was on the form, linear or not. So we said yes. Based on the first plot, we said yes, it is the functional form that whatever I've assumed is okay. So, and the second plot that we saw, the QQ plot, helped us justify our assumption, saying that the residuals are normally distributed. And the third plot that we had, which was on the variance part of it, so whether the variance of the residuals is constant, that means it's not changing as I move higher on my predicted values, right? So, and the last part we used to check whether there are any outliers in the plot. So simple outlier doesn't bother us, but if that data point becomes influential, then I need to take care of it, right? So all of those 4 assumptions are satisfied. We have checked them through this residual analysis. So what I'm basically now concluding is saying that my simple linear regression, whatever I have built, okay, is validated. That means this model has practical applications. I'm not going to use this for prediction. We are going to learn prediction with the multiple linear regression part. So let's get into the next aspect, multiple linear regression. Quickly read through the content on multiple linear regression. So it's an extension of simple linear regression. In SLR, remember, we handled only one independent variable. Now we are going to bring in multiple independent variables. So multiple linear regression is a statistical technique for finding existence of an association relationship between a dependent variable, one dependent variable, and several independent variables. Get out of the habit of referring them to as a dependent variable and independent variable. Dependent variable, you should be calling it as a response variable, and independent variable more specifically as the predictor variables. So you see the functional form, it's an extension of whatever was SLR. So instead of simply stopping it at beta 1 x1, we will have multiple x's, right? So if you look at that equation, we say y is beta naught plus beta 1 x1 plus beta 2 x2, as many variables as you have. In general, p is the number of predictors, of course, plus closing with the error term, right? So all those x1, x2, x3 are your various independent variables. The beta naught is the constant, beta 1, beta 2, etc. up to beta p are partial regression coefficients. Underline the word partial there. They are not regression coefficients, they are partial regression coefficients. And E is my error term. So in MLR, the regression coefficients are called partial regression coefficients, since the relationship between an explanatory variable and the response variable is calculated after removing the effect, in technical terms, after partialing out the effect of other explanatory variables. That is where the word partial is coming in into partial regression coefficients, right? So when I'm establishing a relationship between one, I am removing the effect of all other explanatory variables. We will shortly see that with an example itself, right? So let me pull out those variables that are of interest to me. So placement dot mlr is what we will call it, and in this placement dot mlr, let me select only those values those columns which I want. So I'm saying go to placement data frame, control shift M, and select all those columns that ends with, yeah, our usual part, underscore p. There's an entrance test percentage also, which I don't want to include in the model, so I'm going to say minus e test p. That is, remove, first I'm saying select all those columns that ends with underscore p, and then out of that remove one of these guys. So I'm saying minus entrance test percentage, right? So let's have a recap on what columns have been selected under placement MLR. Alright, so I have SSC percentage, I have the HSC percentage, I have the degree percentage, and I have MBA percentage. So I'm going to use, we have only used degree with MBA. Now I'm going to use SSC, HSC, degree with MBA. Alright, so if you want to, remember I'm skipping certain of those things which I don't want in order to save time. Before I go into regression, if you would want to understand how is the kind of correlation between all my variables, so let me say go to the placement regression MLR file and show me correlation between all the values that are there. So if I simply come back to this MBA percentage part, so MBA with SSC there's a correlation of 0.38, MBA with HSC there's a correlation of 0.35. This we saw. MBA with degree is 0.40. This is what we did in SLR. Right, so fairly good correlation. Earlier, if you recap, if you remember, we have also tested whether this are significant using the core.test. Let me not get into that discussion now. Alright, and now before we build the multiple linear regression model, let's get introduced to one new part here, which we say we are dividing data into two parts. That is, this 215 values that I have, I'm going to divide it into two sets. One is called as a training set, and the other one, for you and me, you can simply call it as a test set, or more technically as a validation set. The idea here is, see, in the previous case we only built a model and we left the story to that. So in MLR we are actually, what we are trying to do is, I'll use a part of this 215 observations to build the model, and after I have my MLR model, I'm going to test it on the remaining part, right? So in order to check how exactly is my model doing when I give it a fresh set of data, right? So what we do basically is, usually we divide it into two subsets. One is called as the training set and the other is called as the validation or the test set. In reality, people, depending upon how much data you have, you could actually divide it into three sets. One is called as the training set, the other one is the validation test set, and the third one would be my test set. So here I'm simply dividing it into two, training set and the validation set or the test set. And how much to have in the training set? Remember, the training set is what is used to build the model. So the proportion of training data set is usually between 70 to 80%, and which I'm going to use. So 70 to 80% of my 215 observations is what we are going to use to build the model, and whatever is left out is what I'm going to use for testing the model, right? So let us do that. Train and test data set. The package that I'm going to use is the CA package. So CA tools. There are several packages which you can use to have these two sets of train and test. I've got used to the CA tools package, so we'll stick on to the CA tools package. I'm only using it to split my data into two parts, the training set and the test set. Now remember, you will have to set seed so that my sample and your sample are same. So I've selected a set, I've selected a seed of 1001. Please ensure you have the same seed, right? So let's create a sample, and what I'm saying is the sample dot split is what I'm using under CA tools. Remember, sample.split is coming from the CA tools package. So I'm saying use the function of sample.split. I'm saying go to my placement MLR dataset based on the MBA percentage and use a split ratio of 0.80. So 80% split is what I'm trying to do. Right. So sample is what has got created logical variable. If you see here, it has basically false and true. So certain of the observations have true and certain observations have false. That means 80%. Since I gave a split ratio of 80%, 80% is labeled as true and 20% is labeled as false. So now what is my train set? I'm simply going to call it as a train set. So in my train set, I'm saying make this train set as a subset of placement MLR, and based on wherever the sample is equal to true. So pick out all those observations against which the sample shows true, put them under train. Let me finish off test, and I'm saying in test make a subset of the same thing with sample equal to false. Alright, so now if you look at your workspace window, the 215 observations that we had have been divided now into something called as a train and test. So train has 172 observations, which is 80% of 215, and the test data set has 43 observations. So what you have basically done using this CA package here is divide your entire data set into two, train and test. Now let's go further and build upon our model part. Right, so let's look at MLR model. Are you referring to the content? So the function LM, the same function LM can again be used to build our multiple linear regression model, and the summary also can be displayed using the summary function. So whatever MLR model I am building, let me store it in an object called MLR model itself, LM function, and I'm saying give me a multiple linear regression model between MBA percentage, the formula operator, tilde operator, followed by a dot. That means consider all other variables. Right, so there are three other variables other than MBA percentage. So dot would take care of that. And I'm saying which data to use. I'm saying use the train data set. Right, so what I'm doing here is building a multiple linear regression model. This is my y, MBA percentage. I'm said consider all other variables. With the dot, I'm specifying consider all other variables. That is, if you recollect, it has SSC, HSC, and degree. And the data that I wanted to refer to is the train data set. So let's build the model, and a small output of my model would basically give us out those regression coefficients, right? So intercept beta naught 36 point something plus 0.06 into SSC percentage plus 0.121 into HSC percentage plus 0.20 into degree percentage. So I've shown you the equation there at the bottom, and let's pull out the summary also, because the summary is what we are going to use for our next part of it. So summary of my MLR model. Alright, so this is my summary, and we're going to interpret on all these values as we did for SLR. But have a look at the equation that I have shown in the content. The regression equation that you have basically built out as MBA percentage is equal to 36.016, that is my beta naught, plus 0.06 into SSC plus 0.122 into HSC plus 0.209 into degree. So you wouldn't want to actually run only the MLR model here. You can get this regression coefficients here in the summary also. It's the same thing, estimate here. Right. So, and how, let's finish off learning how to interpret all this regression coefficients. So the partial regression coefficients, remember in MLR you refer to them as the partial regression coefficients. The partial regression coefficients provides the change in the response variable for a unit change in the explanatory variable when all other explanatory variables are kept constant or are under control. So if I take the first one, 0.062, what exactly, or how do I word it, how do I explain, or how do I interpret it? For every 1% increase in SSC, this is against SSC, for every 1% increase in SSC, the MBA percent will increase by 0.063% provided all other variables. What are the other variables in the model? HSC and degree are held constant. That's why the word partial comes in. Right. Once again, for every 1% increase in SSC, the MBA percentage will increase by 0.063%. You can't stop at that. You're going to say provided all other variables are held constant. That is why the word partial is coming. And since all these variables that I have, SSC, HSC and degree, they are measured in the same units, that's percentage. If I compare those three values, I can basically say that the degree percentage has a higher impact on MBA percentage as compared to others, because this value is 0.06, this is 0.12, and for degree it is 0.2. So 0.2 is the highest. So we can say that degree percentage has a higher impact on the MBA percentage compared to SSC as compared to HSC. I can say this directly from here because remember SSC, HSC and degree are all measured in the same units in this case. So if the unit of measurement is different, we can't straight away decide based on these values. We will need something called as a standardized regression coefficients. So let's keep on that part as of now. Right. So my what we have now is the multiple linear regression. Can I use this multiple linear regression? Yes, but before you want to use this multiple linear regression, you will have to validate it. So only if the model gets validated, I can go ahead and use this model for prediction and other practical purpose. So let's get into on the same lines, whatever we used, those points that we used for SLR validation, similar points is what we are going to use for MLR validation. So the first validation that I'm going to do is validation of the overall regression model using the F test part. Keep this output in front of you. So this is what I'm referring to, the F statistic. This will this is basically going to tell me in terms of is my overall model valid. So ANOVA is what we are going to use based on F test part. So the research question that we are trying to answer here is, does the regression model contain at least one predictor variable useful in predicting the response variable? So is there at least one variable which is useful in predicting my model? So ANOVA is used to validate the overall regression model, and usual way in which we had framed null and alternate earlier when we spoke about ANOVA, same things. So in null you are saying all regression coefficients are 0, that is there is no significant relationship between the predictor variables and the dependent variable. So beta naught equal to beta 1, all of them are zeros. And alternative, you are saying not all coefficients are 0, right? So I am first checking whether my overall model is valid. And what do you conclude? As usual, based on the p-value. So if you look at the p-value in our case, we see that this p-value is less than 0.05, right? So which is highly significant, and hence we can reject the null hypothesis. The p-value here very small, almost 0, right? So less than 0.05 in general. So this means that at least one of the predictor variables is significantly related to the response variable. So when you are rejecting the null hypothesis, look at your null hypothesis. Null hypothesis was all those regression coefficients, beta naught, beta 1, beta 2, etc., as many as you have, are zeros. So now since you have rejected it, you are saying at least one of the predictor variables is significantly related to my MBA percentage. That's my response variable. Right. So since this is the statement in the alternative hypothesis that not all betas are 0, so here there's also a possibility that some coefficients may be 0. So alternative hypothesis simply said that not all betas are 0. That means you also understand that some may be 0. So I cannot simply stop at this, and this is the whole reason why we have to do the t-test to check the existence of statistically significant relationship between individual explanatory variables and the response variable. That is, it is not enough if I check for the overall model being significant or not. In this overall model, there could be certain variables which are significant and non-significant. That is where we'll have to get into. Right. So if you have, there's one small note there which says we usually don't worry about the p-value for the constant. Read through it. We have been discussing about this. Beta naught is not of much significance to us. So let's go on to the second validation part, which basically says the statistical significance of individual variables in my MLR using the t-test part. So within an MLR model, we want to know whether a particular independent variable is making a useful contribution to the model. So in our case, there are 3 IVs, 3 independent variables. So is any of these 3 variables making a significant or useful contribution to the model? That is, you given the presence of other independent variables in the model, does a particular variable help us predict or explain the dependent variable? So the t statistic is again used to check whether or not there is a significant association between the independent and that concerned variable, dependent variable. That is whether the beta coefficient of IV is significantly different from 0. So usual way for the null and the alternative hypothesis for a t-test, in null we are going to say there is no relationship between that particular independent variable and the dependent variable. So in null basically we are saying beta I in general is 0, and alternative two-sided we are saying beta I is not 0, that is, it is significantly different from 0. So when we cannot reject the null hypothesis for a particular independent variable, we would be saying that we do not need that variable. So if I say for a particular variable x1, if I cannot reject the null hypothesis, that means what I mean to say is I don't need that variable x1 in my model, given that the other variables like x2 and x3 will remain in the model. So let's look at, I'm not looking at the t values, I'm looking at the p values. Look at the p values of SSC, HSC and degree percentage. So what do we see? We see that for SSC percentage, right, this particular value, so SSC percentage is not significant at 0.05 alpha. So it so happens that what we do is for a fixed HSC percentage and degree percentage, we say the changes in the SSC percentage will not significantly affect my MBA percentage. Right. So for HSC and degree, since the p values are less than 0.05, you tend to reject the null hypothesis, whereas for SSC percentage you are not able to reject the null hypothesis. That means whatever is that concerned beta 1 in this case will be 0. So retain the null is what we are saying. So in null we had said beta 1 is 0. So SSC percentage is not going to make a significant contribution into the model which already has HSC percentage and degree percentage present in it, is what we are saying. So if it is not going to make a significant contribution, yeah, as you would have guessed it, what are we going to do? We are going to say, let me remove that variable. So let's end up removing the variable. You're very clear now on what basis I am removing SSC percentage, because it is not significant. Right, so let me build a fresh model. Let me call it as MLR. We are going to build multiple models. So let me call this as MLR model 1, and this MLR model 1 that I am building now would be between MBA percentage, and I'm going to specifically select only the remaining. What is remaining? What is remaining is HSC percentage plus degree percentage. Alright. And I am saying use these two variables only to fit the model and use the train data set. Right. So my MLR model 1 is ready. Let's look at MLR model 1. Right. So now your model has only HSC and degree. We have removed SSC because it was not significant. It was not able to contribute when these two other variables were present in the model. So if you read through the regression line, MBA percentage is equal to 36.43. This is my beta naught, and now this is my beta 1, 0.142, and this is my beta 2. Right, so 0.246. Clear with the MLR equation? Right. So what we say is a good regression model should include only significant independent variables, and in general, it is not always clear what will happen when we add or remove variables from a model. So what we did here was we removed off SSC. So in case you have a model, because we removed only SSC because that was the only variable which was not significant. What if there are other insignificant variables? So you shouldn't be removing all the insignificant variables in one shot. I've given you a brief explanation there. So we say therefore we should not consider dropping all insignificant variables at one time, but rather than that take a more structured approach. That means I would do an automated approach, and those automated approaches are basically by the names of forward selection, backward elimination, stepwise regression, best subsets method, etc. So what these methods ensure that only statistically significant variables for a given alpha would get included in the model. So instead of you manually putting here HSC and degree, if I use this say stepwise regression model, it will only incorporate those variables which are going to be significant, right? So we are not touching upon those automated methods as of now. So we included all the three, and we realized SSC is not significant, so we removed SSC, and then we ended up including the remaining two, HSC and degree. All these automated methods are very useful when you have multiple independent variables, and that too you realize many of those independent variables are insignificant. So you can't be doing that trial and error method of removing one and adding one and seeing what happens, right? So in this case this method was okay because there was only one insignificant variable out of those three that we are considering. Alright, so moving on to the third part, the coefficient of determination part. If I go back to my output from the summary, I have not run summary on this. Let me finish off running a summary of MLR model. Right, so if you once you run the summary part of it, this is only on those two variables, right? So whatever we have considered, you tend to realize overall model is significant. The remaining variables that have HSC and degree, they are also significant. All right. So as we used to understand the meaning there, let's come and first finish off the third validation part, understanding R square. So coefficient of multiple determination, R square, or the adjusted R square value is what we are looking at. So as you understood, R square measures the proportion of variation in the dependent variable explained by the model. Now I was just telling you with SLR, we only looked at the simple multiple R square. We didn't bother about understanding adjusted R square, which we'll see now. So a problem with this R square is it will always increase when more and more variables are added into the model, regardless of whether these variables that you're including, whether they are statistically significant or not. Right. So the more independent variables you add into the model, this value of R square has a tendency to increase. So to overcome this drawback is where we look at this adjusted R square. So this is the solution to adjust the value of R square by taking into account the number of predictors. So the adjusted R square that you see here, the adjusted R square reflects both the number of independent variables and the sample size. So it is, as it says, it is adjusting for the number of independent variables that you've used to build the model, and also the sample size that I've considered. So adjusted R square will increase or decrease depending on whether an independent variable is added or dropped, thus giving an indication of the value of adding or removing the independent variable in the model. So if there's an increase in adjusted R square, it's an indication that the model has improved, right? And in general, remember, the adjusted R square value will always be less than or equal to uh, the R square value. Alright, so in this case, I'm going to interpret based on my adjusted R square. Marginal difference, right? So should I bother about this difference? Yes, because adjusted R square is basically adjusting for the number of variables that you have used into building the model. The more variables you keep bringing here, R square would invariably increase, right? So it is not good for me to rely on R square, so I'm going to rely on the adjusted R square. It has been adjusted for the number of variables, in short. So in our example, what is the adjusted R square that you see? We see an adjusted R square of 0.2328. So when I talk in terms of percentage, what it means is 23.28% of the variability in MBA percentage is explained by the model. So whatever model I have built uh, between MBA using HSC and degree, this model is able to explain 23.28% of the variability in MBA. Remember, this R square was around 16% in SLR. So in SLR we had only degree percentage. So on its own, degree percentage was able to explain 16% of the variation in Y. Whereas when you club it with HSC, both put together, HSC and degree, they are able to explain 23.28% of the variability in Y. Alright, so that is all how you interpret the adjusted R square. The fourth part, the residual analysis, the same usual 4 plots that we saw with SLR is what you will get here. So remember, the model that I'm using is MLR model 1. I've discarded the plain MLR model. So the 4 plots of the MLR model, I finished generating those 4 plots, and if I look at those individual plots, remember, those 4 assumptions is what these plots are checking. Right, so I'm not going to go through in detail explanation of those 4 assumptions. The first plot basically talks about whether the functional relationship has been correctly specified or not. So we assumed a linear relationship. So when I look at the first plot, based on which I'm able to say yes, the linear relationship assumption is satisfied, because I don't see any pattern in my residuals, right? And I have a fairly horizontal red line. So that assumption gets satisfied. The form of regression, it is linear. The second plot is to do with the normality assumption. The residuals, are my residuals normally distributed? Yes, few here and there at the top and the bottom, not to worry about. Majority are on the dashed line, so I can broadly say they are approximately normal. So the residuals are normally distributed is what I'm going to conclude with this second plot. What is the third plot now? The third plot is the scale and the location plot. So with the scale and the location plot, we are checking for homoscedasticity, that is whether the variance of the residuals are homogeneous, homoscedasticity. So what do you conclude? Right, so it's again you see a horizontal line, almost horizontal, with equally spread points, right? So there is no shape that you are seeing here. I told you, remember, it will come out as a kind of funnel shape, the tilted funnel, if there is some variability in the variance. Alright, so the third assumption also gets satisfied, and the last assumption was to do with what? Let us pull out the plot. The last assumption was to do with the residuals versus leverage, to check whether there are any outliers, and if at all those outliers are any influential. So first part we said outliers which exceed 3 standard deviation. I don't see, this is my 3, closer to it, but as long as it's below 3 my job is done. And on the bottom side absolute value. So all my uh, outliers do not exceed the 3 standard deviation. And leverage part also, if you calculate, remember the formula to see whether an observation is highly leveraged, 3 into p plus 1 by n. So p is the number of predictors. In this case its number of predictors is 2, so 2 plus 1 3, 3 2s are, sorry, 3 3s are 9, 9 by whatever we had, some in the train data set I think we have 172, so 9 by 172, whatever is that value, you will realize all those data points are well within that calculated value part, right? And Cook's distance part I told you, which we'll be using to see whether there are any influential observations. The influential observations would be on uh, extreme right top or at the right bottom. So this is the Cook's distance line. Right, so there are no points which are basically influential. So this is that red dashed line that we said we could not see earlier. Here also you see that red dashed line only at the top, not on the bottom side. So in broad you are able to conclude that my data doesn't present any influential points, right? So this is where all those 4 residual plots are used to do our validation part of it. Alright, so residual analysis and done, the 4th part of it. The last part, the 5th part, is to do with something called as a multi-collinearity and the variance inflation factor. Now it so happens that when our data has large number of independent variables, it is always possible that few of these independent variables may be highly correlated with each other. Right. So in our case we had only 2, degree and HSE percentage, but when you have large number of independent variables there is a possibility that there will be a high correlation between those independent variables. So existence of high correlation between independent variables is what is called as multi-collinearity, and presence of multi-collinearity can destabilize my MLR model. So due to presence of multicollinearity, what would happen is it is possible that some variable may get labeled as insignificant because the p-value gets inflated, or the sign of the regression coefficient may turn out to be negative. So what I'm trying to say is something like if there is a huge correlation between independent variables, you might see that if I put a minus sign to this degree percentage, it is very difficult to digest saying that if degree percentage goes up, MBA percentage will go down, right? So that could happen when you have this multi-collinearity, that is high correlation between independent variables. So it becomes necessary to identify the presence of multi-collinearity, and if it is there, I need to take some corrective action. So how do I assess this? Multi-collinearity can be assessed by computing a score called as VIF, the variance inflation factor, for each of the independent variable. The smallest possible value of VIF is 1. Value of 1 would indicate there is no multi-collinearity, that is absence of multi-collinearity. As a rule of thumb, a VIF value that exceeds 5 or 10 indicates that there is a problem, and VIF greater than this would require further investigation to assess the impact of multi-collinearity. And if at all we come across this multi-collinearity, how do I overcome this? You will study all these models that I mentioned there in semester 3. So the remedies to handle multi-collinearity include principal component analysis, ridge regression, lasso regression. Hold on till semester 3, you would come across all these things. So how do I calculate the VIF part? You can use that VIF function which is available in the car package that can be used to detect multi-collinearity. So I will need to first install the car package. quite big. Shouldn't take much more time. All right. So remember, if you what you could do is to, okay, let me finish of this and then I'll come back to the explanation. So let's activate the car package. This car package has this function called VIF, variance inflationary factor. What I'm saying is do this on my MLR model 1. Alright, so look at your output. The VIF for HSC is 1.2 and the VIF for degree is 1.27. We said earlier the smallest possible value for VIF is 1. So that indicates absence of multicollinearity. So I don't have that problem in my model, the multicollinearity problem. What you could do is, if you remember, we were using this mutate of dplyr to create an additional variable. Just to understand the effect of multicollinearity, what you could do is, I have only two variables in my model now, that is the degree percentage and the HSC percentage. Use the mutate function to create a third variable, right? And let us say the third variable is simply an average of your HSC and degree. So use the mutate function to create an average percentage variable. Let this average percentage variable be the average of HSC and degree. Now since it is average, if you go ahead and calculate correlation, you will try to you might find that this average percentage has a high correlation between either degree or with HSC, and then try again building a model. You might see a multicollinearity effect, right? Or and as simple as, you have a degree percentage thing, create one more new degree percentage, and let us say this new degree percentage is simply 5% plus the degree percentage. So you're simply adding 5% and creating a new variable called new degree percentage. So if I take the correlation between degree percentage and this new degree percentage, it will be invariably high, because the new degree percentage is simply 5% plus whatever is my existing degree percentage. You'll be able to clearly see the effect of multicollinearity there, right? So I don't want to get into that now. So my all my validation part has been taken care of, right? So we had, if you turn back to those pages, there were those 5 things that I wanted to check upon in order to validate my MLR model. And since on all these 5 points I have validated it, what can I do with this MLR model that I have built? The MLR model that I have built can be used to make predictions, right? So this is the whole purpose. And remember, I'm going to predict on test data. Right, so using this trained data, using this 172 observations is what I built my model. So I need to test whether this model that I built, when I give it a new data, I have not used this 43 observations in building the model. So how is this model going to function on unseen data is what you are doing here, predictions on test data. So let me calculate. We'll call this as MBA pred. What we are saying is use the predict function, and use the MLR model 1 on the test data. So what I'm basically saying is apply this model 1 that I've built on the test data set and predict, right? And whatever the values get predicted, I'm storing it under MBA predicted, right? So let it predict on the test data set, and if I convert that in terms of a data frame, so in one column I'll have my, remember in the test data set I'm going to pull out my actual MBA percentage. This is in the test data set, what is the MBA percentage actual values versus what are the predicted values. This is for all the 43 observations, right? So this is my observation number 1, student number 1. These are random of those 43 values. So for the first observation, this particular student, his actual MBA percentage was 58.8, and my model has predicted it to be 63.3 something. One more for student number 6, my actual MBA percentage is 51.5, whereas my model is predicting that to be 60%. Remember, I've used my model on a test data set. When I built the model, it had not seen these observations, it has not seen these students. So it is on this 43 observations that I'm predicting. Right? So yeah, this is fairly okay. On certain observations that is doing fairly good, on certain observations that is not doing that good. So what do I do with that? Right. So how do I know, is it doing good, bad, dirty, ugly? Let's keep it to the next part. I have taken enough for this session. I hope you enjoyed this online mode. You don't have a choice. You would have access to my email ID. So in case you have any specific queries, you can either share the screenshot or drop me a note, and I should be able to help you out. You will get an info as and when I finish off recording the other part of it. So a very small part that is left out. In the sense, in MLR, the small part that is left out is I want to check, I want to test how this is working. I know in some cases it is good, in some cases it is not that good. So overall, how is it performing? That small part is left out. And once we finish that, we are going to get into the logistic regression. That would be the last part of your syllabus. All right. So do well. Right. Good luck.